What's up, guys? In this video, I want to go over my top 3 examples of functions that are not obviously even or odd. Typically, when we're first learning about even and odd functions and we understand the symmetry, looking at a graph starts to make sense. You do a couple examples and you start to get it. Then we move on to polynomials and we start with the basic examples, and then we add in ones that have like x squareds and x cubes and x's and constants, and we start to see the patterns and we're able to identify them rather quickly. But then we start moving on to functions where it gets a little bit confusing to our natural eye to be able to understand if a function is even or odd. So that's exactly what I wanted to cover in this video. So let's go and take a look at the first function that a lot of students will just not obviously understand if it's even or odd. And sometimes if they don't understand, and let's say it's on a test or a quiz, they might make a guess. For the sake of time, they're like, I'm not going to go through the rules. I'm just going to try to look at my powers and just say, oh, well, I think this is going to be an even or an odd based on what I know from either the graphical approach or from polynomials. So this is not a polynomial because the square root kind of ruins that. But let's go back and do a quick little review of our even and odd rules so we can remember how we're going to test this function to see if it's even or odd, and then we'll actually go ahead and test it. So remember, to test for even and odd functions, what we want to do is take our function and plug in a negative x. If we get back the original function, then we know that function is going to be even. If we plug in negative f of x and we get the opposite of our function f of x, then we know that function is going to be odd. Now, a mistake that students will make for a problem like this is they'll say, oh, I can take the square root of 2 and I can take the square root of 1. So that would really be an x. And therefore, if I'm testing this function, I have a x times x or x cubed times x. That'll give me x to the fourth. This has to be an even function. Or if they test it separately, somehow like add in a plus or a minus here, just kind of start making things up, they might come into it being an odd. But the main important thing we want to do, ladies and gentlemen, is test it. So let's plug in negative x and see actually what we get. Now, again, remember, it can be even, it could be odd, or it could be neither, right? That is a possibility as well. So when I plug in a negative x, I'm going to have a negative x raised to the third power, and then I'm going to take the square root of a negative x quantity squared minus 1. All right, so remember, anytime you have a negative number or variable raised to an odd power, that is going to remain negative. So negative x cubed is negative x cubed. Negative times 4 is now going to turn us to a negative 4x cubed. Under the square root, again, we cannot take the square root across addition or subtraction. So I'm just going to have to simplify this and leave it here. Negative x squared is simply going to be a positive x squared, and there's nothing I did with the negative 1. So actually, the radicand is preserved in this case because I had this even power. Now, if I factor out a negative, the important thing to remember is you can't factor out a negative from both of these because they're not separated by addition or subtraction. Think about it this way. If I had a minus b, I could factor out a negative, right? That'd now be a, if I factor out a negative from there, it'd be a negative a plus b, right? Because you can always apply distributive property backwards. But if I have a negative ab and I factor out a negative, I can't factor the negative across both of them because they're separated by multiplication. So this is simply just a negative a times b. That's just another way you can write it. But you don't apply distributive property in this case because they're separated by multiplication. You would just write it as a negative ab. Whereas here, you need to make sure you multiply the negative times the a as well as times the b because they're separated by addition, and that works the same if they're separated by subtraction. So since these two expressions are separated by multiplication, when I factor out a negative, it's just going to simply be a positive 4x cubed times a square root of x squared minus x. So going back to our rules, you can see that this is our original function. This is going to be our f of x, and we are able to factor out a negative. So it's negative f of x. So therefore, ladies and gentlemen, this is an example of an odd function. All right, now let's go and look at number 2. Now, number 2 is going to be something that's rational. So we'd have f of x is equal to a 16 over a x cubed minus x. So the important thing about this to remember is actually, let me actually go back to this original equation, because the reason why this makes it odd is whenever you're dealing with a radical, you can't factor out a negative from the square root or a cube root or anything like that. So the reason why what's important about this is we need to, whatever's outside the radical either needs to be preserved or be the opposite when we plug it in. In the inside, if this was turned into a negative, then it would be a neither even or odd. But since it was preserved, I could focus on the negation of the outside. When we're dealing with a f of x function, or we're dealing with a rational function, the same thing. We want to make sure that whatever either our numerator, if our numerator is preserved, but our denominator is the opposite, then we can rewrite that as a negated segment or a negated function. Or we could either have our numerator and our denominator both be preserved, and then we know it'd be even. So let's go and take a look at this one. And again, go through plugging in the information. So if I take a f of negative x, I can't do anything in the numerator, so we know that's going to be preserved. So the only way that this is going to be odd is if my denominator is negated, or it's going to be even if my denominator is preserved. But hopefully you remember from polynomials, this is not going to preserve my denominator, because when I plug in a negative x, right, what's going to happen here? Well, negative x cubed is again going to be a negative x cubed. And negative x is just going to be negative x times a negative is going to be a positive x. Now, again, this gets students confused because they got to get confused as far as how we can rewrite this. So there's a couple important things that I want you to remember. If I had a fraction like a negative 3 over 4, remember, I can rewrite that as a negative 3 over 4. I can rewrite that as a 3 over a negative 4. The only thing I can't do is rewrite that as a negative 3 over negative 4, right? So what's important about this is if I have a negative on the denominator, I can rewrite that in front. That's important because that's the notation we are seeking. The first thing I want to do is say, well, can I factor out this negative? So we take in the denominator, we say, all right, let's factor that out. By factoring out a negative out of both of the terms, right, distributive property, factoring this out, that's going to give me a positive x cubed minus an x. Now I can take this negative, just like pretend it was right here, and I can rewrite it in front. So therefore, my final answer is going to be a negative 16 over a x cubed minus x. So we have a negative times a function. You can see this function is again going to be preserved. So it's the opposite of my function. So therefore, this is going to be odd. Now, ladies and gentlemen, I didn't want to just always pick odd functions, but I also want to go through maybe something with even that might be obvious. So let's go and take a look at the last function, which would be f of x equals a x cubed absolute value of the cube root of x squared plus 1. Okay, remember, if it's going to be even, that means my numerator and my denominator have to be preserved when I plug in a negative x. Now, obviously, we know if something's being raised to an odd power, that's going to negate it. But the important thing here is we have this absolute value. We know absolute value, if we think about the absolute value function, that's also going to be that's always going to be a even function. So, but again, let's go ahead and test things. Same thing with the cube root. We know the cube root is an odd function, but again, if we can get everything preserved in this denominator, we're going to be good, which in this case is going to be an x squared. So I plug in a negative x, and what we're going to have here is the absolute value of negative x cubed. That's not supposed to happen. Negative x cubed divided by the cube root of a negative x quantity squared plus 1. So negative x cubed is a negative x cubed, but the absolute value of that is simply just going to give me a x cubed. And then divided by, over here, what I'm going to have as a positive x squared plus 1. And again, we can keep that absolute value there. And what I want you to be able to see is these are going to be preserved. So ladies and gentlemen, when I plug in this negative, I get the exact same thing as going to be my original function. So therefore, this is an example of an even function. Now, one thing that you can always go ahead and do, ladies and gentlemen, is look at the graphical approach. So therefore, you can visually understand when you are applying your algebraic properties to make sure that a function is even or odd. But nevertheless, I hope these 3 examples helped you out. And now you have much more confidence to be able to identify if a function is even or odd on your own.